Welcome to section C3, where we discuss some trigonometry. Now, we really need to focus on our ability to do the trigonometry, the trig functions or ratios, and we're going to spend a good amount of time doing that in section C3, but it's almost like a trig course in one day or one section. So we're going to squeeze a lot in, but these are things you've seen before, hopefully. First thing I want to start off with is a definition of just what is an angle. Start off with the definition of an angle, and then we'll talk about how to measure those angles both in degrees and radians. So let's get started. So first thing is, how do we measure an angle? And we define angles on a circle. It's a great way to define an angle. So we'll draw a circle here. We'll put the origin here, and then let's use the positive x-axis as the initial ray. Now, they call it an array, and so that means it does kind of go on forever. We'll put an arrow there to indicate that it goes on forever. What I want you to do is rotate that initial ray counterclockwise and then stop, like a minute hand on a clock. And then you're going to stop at the terminal ray. You just created your first angle, theta. We use Greek letters to denote our angles, and we measure our angles using degrees. There are 360 degrees in a circle. So, if we were to measure backwards, what happens? This, by the way, is a nice positive angle. We draw another circle here. We put our initial ray here, but this time let's go backwards. And let's stop about here. You still have an angle, but it's a negative angle. In fact, if I were to draw this vertical line down, I'm going to say that that is right in the middle, and we'll call this negative 45 degrees. Because there are 8 of these in a circle. 1, 2, 3, 4, 5, 6, 7, 8. So 360 divided by 8 is 45, but we went backwards, so that's a negative 45 degree angle. Now, the other thing I want to talk about are coterminal angles, angles that share the same terminal ray. So we're going to establish an initial ray here again. I'm going to rotate the counterclockwise, so this is going to be a positive angle, and let's go to 45. So I'll put a vertical line here, and I'll go right down the middle, so I get a nice clean 45 degree angle. This is theta. So theta is equal to 45 degrees, an eighth of a circle. But what if we continue this process, and you take this minute hand, and we keep going? What's this angle worth? Well, if you think about it, the terminal ray has encountered the initial ray, so it went a full trip around the circle, and then it went 45 extra degrees. So in reality, this one would be theta 1. This is theta 2. It's a different angle. It's 405 degrees. They're considered to be coterminal because they share the same terminal ray. Now we have to be careful because coterminal angles are different angles. One of them's 45. One of them's 405. I mean, if this were temperatures, it's certainly different temperatures, right? 45 degrees versus 405 degrees is very different. So they are different angles, there's no question. But because the terminal ray is in the same location, it's hard to tell the difference between these two angles when it comes to the trig functions. In fact, the trig functions really don't care how big or small that angle is. It doesn't even care how the terminal ray got into that position. It just cares that it's in that position. So we're going to look at some coterminal angles and how the trig functions are affected by those shortly. But first, I'd like to discuss a different form of measurement called radian measurement. Now, radian measurement is used for angles. It's not a linear measurement, just like degrees are used for angles. And I think the most useful thing to note will be the definition of 1 radian. If I were to take a circle, and I were to take 1 radius off that circle, right here, and make it a string. So we take 1 radius as a string, and I were to stretch it along the outside of the circle, which we refer to as the circumference. Certainly the string has a fixed length, whatever r is, and it will come to a stop right there. So this is also r, but it's kind of a curved r. We've stretched that string along the outside of the circle. If you do that, you have formed an angle, theta. The measurement of that angle in radians is 1. So that's the definition of a radian. And it doesn't matter what the size of the radius is. This could be 2 inches, this could be a light year, and that angle will be the same. It'll be actually the same size. And it kind of looks about 50, 60 degrees, somewhere in that vicinity for degrees. Now, if I were to continue this process, and I'll do it here on another circle, and it's not a unit circle, it's a circle of radius r. It can be any radius you like. So let's do this. Let's do 1 radius string here. Let's do a second radius string here. Let's do a third radius string there. So how many radius strings did we get so far? 1, 2, 3. Let's do another one. There's a 4th one there. There's a 5th one here. And a 6th one here. So 1, 2, 3, 4, 5, 6. And a little bit of excess left over. So how many radians in a circle? Well, that means this is theta that went around the entire circle. The first radian is here. The second radian is there. The third radian is there. 4th one there. 5th one there. 6th. So you've got about 6 of them. In fact, there's 6.28 radians. So there's your little 0.28. I guess the real question is, well, why is it 6? And where's the 0.28 coming from? And I put ... because it keeps going on and on. So here's how we figured out how many radians are in a circle. It turns out that the measurement along the outside of the circle matches the measurement of the radian angle inside the circle, doesn't it? So 1 radius string, 1 radian. 2 radius strings, 2 radians for the angle. So I guess let's just measure the circumference of the circle. The circumference of the circle means let's measure all along the outside here. Remember the formula? So if the radius is denoted by r, the circumference of the circle is 2 pi r. The circumference of the circle is 2 pi radians, or I'm sorry, times the radius, which 2 pi is roughly 6.28 times the radius. So how many radius strings fit on the outside of a circle? 6.28 radius strings. That's how many r's are represented on the outside. But remember, the number of radius strings is a match to the number of radians. So theta for a full circle is exactly 2 pi. And mainly it comes from the formula for circumference. That's where we get that from. So we want to be able to convert back and forth between degrees and radians. That's really the most important thing. By the way, I understand that converting to a new unit of measurement can be difficult. It's like trying to think in kilometers or centimeters, where we think in miles, we think in feet, and we think in inches. We think in degrees, and degrees are really a unit of measurement, a construct for us to think about. But math natively thinks in radians. You'll find this as you go further into calculus, that as we look at some of the formulas used in calculus, as we solve for theta, we solve for the angles, it seems to come out in radians, not degrees. So we really need to get comfortable with radians, and we really need to be able to convert from degrees to radians and vice versa. So the way to do that is to recognize that there are 360 degrees in a circle, and there are 2 pi radians in a circle. Now, it's even better to look at half a circle. So a half circle has 180 degrees in it and pi radians. We can use that to convert back and forth. So remember that 45-degree angle? How many radians is that? Now, in order to convert any units, you want to use this thing, which is referred to as a unit conversion fraction. And what you want to do is put the units that you don't want down in the basement here. Now, we don't want degrees. The new units, put them on top. Now, use an equivalent measure of each, and I don't care if you use a full circle or a half circle. Best to use a half circle, though there are 180 degrees in half a circle, and there are pi radians in half a circle. Notice that the degrees cancel. I want you to reduce this fraction. By the way, this is the same as 45 over 1. You multiply across. Multiply straight across, multiply straight across. There's no more degrees. But take a look at that 180 down there. 180 is 45 times 4. So, how many radians in 45 degrees? There are pi over 4 radians. In fact, that's not even a full radian. That's about 3/4 of a radian. So 1 radian is pretty big. Remember, it kind of measured up and looked around 50 or 60 degrees. So 45 degrees naturally, therefore, is less than 1 radian. It's about a little more than 3/4 of a radian. Let's convert back. Let's take pi over 6 radians and go into degrees. So remember, you multiply by a unit conversion fraction. We want to throw away radians now. We don't want those anymore. I do want degrees, and you can use half a circle. There are 180 degrees in half a circle. There are pi radians in half a circle. But check this out. Not only do the radians cancel, the pi cancels too. So we end up with 180 degrees over 6, which is 30 degrees. So it's a little easier, I think, to convert radians into degrees. In fact, it's even easier than what we just did. Check out this pi over 6 radians one more time. In fact, pi over 6 is about half a radian, so it should have been smaller than 45 degrees, which it is. It's 30. But if you just circle this one piece of it, recognize that pi radians is half a circle. It can be just instantly replaced with its equivalent, 180, and the divide by 6 is still there. So that is the quickest way to convert from radians into degrees. And that's to basically replace pi radians with 180 degrees. Replace pi with 180. Now certainly pi is not 180. Pi is 3.1415. This is just for conversion purposes. Okay. The last thing we'll talk about in this video is the Arclength formula. Now, the Arclength formula is one of the easiest formulas in trigonometry, although it's often misused. So let's talk about what Arclength is and how to use this Arclength formula. So Arclength. The Arclength is a piece or just a component of the circumference of a circle. So if I were to draw a circle, and we were to come over here and draw in a radius, the arc length is just a little piece of this arc, of this circumference. This is an arc length. It's a curvy measurement. We label that arc length S. And of course, take a look at what it does. It forms an angle. Now, we all know that's not 1 radian because that is not the same length as the radius. But it's calculated as S equals just r theta. See how easy that formula is? But there's one very important sticking point, and that is theta must be in radians. Theta must be in radians. So, let's calculate an arc length. Let's use something familiar to us. Let's use a pizza. So we're going to take a 10-inch pizza, and we're going to slice it up into 8 slices. So here's our 8-cut pizza. And what I'd like to know is, what is the length or arc length of the crust of this pizza? If it's Domino's, let's say, they want to know what that is because I know they put various things in the crust. They put cheese in the crust. They do all sorts of things that they'd like to know. Hey, one slice of pizza, what's the length? We already know the radius. But what's the length of the crust if we were to measure it, which would tell them how much or how many ingredients they would need for that. So, first of all, I'm not going to give you the angles on this. We need to figure that out. This is a pizza. This is a circle that has 360 degrees. You just sliced it into 1, 2, 3, 4, 5, 6, 7, 8 equal slices. Well, it follows that each slice must have a 45-degree angle. That would go right here. Now watch what happens if we forget to convert this. S equals r theta. 10 inches times theta, 45 degrees. 450 inch degrees. Not only does the number not make sense, that does not look like 450 anything, but inch degrees is not a valid unit of measurement, really. So we'll cross that off. What we forgot to do was convert to radians. So let's convert 45 degrees into radians. Here's my theta is 45 degrees. Let's convert to radians by multiplying by unit conversion, fraction, degrees on the bottom, radians on the top. There's 180 degrees in a circle. There are pi radians in a circle. Cancel out the degrees, and we get 45 pi radians on top, and 45 times 4 is 180 on the bottom. So theta is actually pi over 4 radians. Pi over 4 is about 3/4. It's less than 1. In fact, radians is such a native unit of measurement that we don't even list it sometimes. Be careful. If it says theta equals 1, it is not 1 degree, it's 1 radian. If it says theta equals 30, it's not 30 degrees, it's 30 radians. So we all have to be on the same page. If there are no units listed, radians are so native to math that we default to radians, actually. So we don't actually need to list the units on this angle. So S is r theta. R is the radius of the pizza, 10 inches. Theta is the angle measured in radians. In fact, it's so native that we don't even list the units. In fact, I'm glad that we don't, because look what we get. We get 10 pi over 4 inches. And if you think about it, we're measuring the arc length, and it should be inches. So I'm calculating what that is right now, and it's roughly 7.85 inches. Now, if we go back to the picture, I think that makes sense. The units are right, because we measure in inches here. And not only that, if this is 10 inches long, yeah, that does look like 7.85 sounds very reasonable. So that's how we use the arc length formula. Hey, one more quick example. Let's say you're driving in a car, and you come up to one of these traffic circles that we seem to have in the capital region here, and you're coming around the traffic circle, and maybe you come all the way and you exit over here. Now, if the radius of that traffic circle were, say, 500 feet, how much mileage would you put on your odometer from here to here? What do you think? Well, formula for arc length is r theta. Okay, so what's r? We got it right here. What's theta? Theta is half a circle. That's pi. So how many feet around the bend there, around our traffic circle? That would be 500 times pi. So I'm calculating that for you right now. 1,570.8 feet. I don't think that shows up on your odometer, so let's make a little quick conversion, find out what's going to happen. It turns out that if that's in feet, my odometer reads in miles. And how many feet are there in a mile? 5,280. So we cancel the feet. And all I really have to do is divide by 5280. So guess what? My odometer will tick 0.3 miles if we round it. So see, Arclength has its applications, and that's another good example right there, traffic circle. Okay, so that completes this video. We're going to move on to 6 trig functions. They're called trig functions. They're also called trig ratios. So stay tuned, and we'll see you on the next video.